In the previous electromagnetism classes, we have learned how charged particles are affected by electric field. So in this chapter, we will study electric fields in matter. So we will start with polarization, then the field of a polarized object, electric displacement, and then self-consistence of electric field and polarization in linear dielectrics. So for the first subtopic, we will tackle dielectrics, induced dipoles, and polarizability, alignment of polar molecules, and the polarization and susceptibility. So matter, as we know, is anything that has mass and occupies space. So everything that we see is actually matter. Matters can be classified as solids, liquids, and gases. But we can also classify matter as conductors and insulators or dielectrics. So conductors are materials that contain a limited supply of charges that are free to move about through the material. So these charges are electrons that are free to move. While in dielectrics, all charges are bound and can only move a bit within the atom or molecule. So this microscopic displacement are not as dramatic as in conductors. There are two principal mechanisms by which electric fields can distort the charge distribution of a dielectric material. So these are stretching and rotating. Okay, so let us talk about induced dipoles and polarizability. The question is, what happens to a neutral atom when it is placed in an electric field? So we might be tempted to say that a neutral atom would not be affected by the presence of an electric field kay neutral nun siya, no? We might be tempted to say that uh, nothing will happen to a neutral atom because the field has no effect on it. But this is not correct. Okay, so although the atom as a whole is electrically neutral, it has protons and electrons. So we know that a neutral atom has equal number of protons and electrons. So in the presence of electric field, the nucleus is pushed in the direction of the field and the electrons in the opposite direction as the field. So, muna siyang mahitabo kung ang neutral atom kay ato ang expose or ibutang siya nato sa region nga ng electric field. Now, if the field is large, it can pull the atom apart completely. So the atom will be ionized and it becomes a conductor. So that is if the electric field is very large. But if the electric field is not huge enough, an equilibrium is established. So this equilibrium is a consequence of number one, the attraction of the electrons in the electron cloud and the protons in the nucleus. So since a neutral atom is made up of uh, sorry, protons and electrons, then those charged particles can attract, no? And then the second one, so to equilibrium is a consequence of first the attraction between electrons, the electron cloud, and the nucleus. And then the second one is uh, the electric field pulling the electrons and nucleus apart. Okay, so the balance leaves the atom polarized. So again, if the electric field is huge, then the atom will be ionized. It will become a conductor. But if the electric field is not huge enough, it can polarize the neutral atom. So the electric field will leave the atom polarized. So polarized means that the positive charges are shifted slightly one way and the negative charges on the other way. Okay? So, if the atom is polarized, the atom now has a tiny dipole moment P, or we can call it the induced dipole moment P, which points in the same direction as the electric field. Okay? And it is proportional to the field. So P, the induced dipole moment, can be expressed as this kinishang equation. It is proportional to the electric field, where this term here, alpha, or the atomic polarizability, is the proportionality constant. Now take note that alpha is dependent on the detailed structure of the atoms. So for example, a primitive model of an atom consists of a point nucleus, such as this one, surrounded by a uniformly charged spherical cloud of radius A. So calculate the atomic polarizability of this atom. Okay, so in the presence of an electric field, this is an external electric field. The nucleus will be shifted slightly to the right. So the nucleus, which is supposedly at the center, will be shifted slightly to the right with a displacement equal to d. So the actual displacement involved is extremely small. So this d here is extremely small. And the electron cloud will be shifted slightly to the left. Okay. Let us assume that the equilibrium, sa ganito na ay equilibrium, the equilibrium is established when the attraction of the electrons in the electron cloud and the protons in the nucleus is equal to the force that is caused by the external electric field that is pulling the electrons and the nucleus apart. So let us assume that equilibrium is achieved when the nucleus is displaced a distance d from the center of the sphere. So at that point, the external field pushing the nucleus to the right exactly balances the internal field pulling it to the left. So that is, so you have this one. The electric field, the external field is equal to the internal field pulling it to the left. Okay, so again, at this point, when the nucleus has moved a distance d, which is very small, the external field pushing the nucleus to the right exactly balances the internal field pulling it to the left. So that is E is equal to E sub E, where kini siya class, E sub E is the field produced by the electron cloud. So again, there are two fields here. One is the applied electric field. We can call this the external field equal to E. And then we have here E, which is due to the electron cloud. Okay, so note that the field at a distance d from the center is equal to this one. So it is equal to 1 over 4 pi epsilon naught q times t over a cube. Okay? Ano ganini? You have, you can get the electric field due to the electron cloud. You have 1 over 4 pi epsilon naught q in over d squared, which is equal to 1 over 4 pi epsilon naught q over d squared multiplied by d cube over a cube. And simplifying this one, this will become 1 over 4 pi epsilon naught qd over a cube. So at equilibrium, since your E is just equal to E sub E, then you have this 1 over 4 pi epsilon naught qd over A cubed that is just equal to your external electric field. Okay? And then take note that P is equal to QD. The induced dipole moment P is equal to Q times D. So you can just replace it, kini siya nga term here, in the numerator by P. So therefore, your E can be expressed as P over 4 pi epsilon naught A cubed. Alright. And then take note that we also have this equation. P is equal to alpha, the atomic polarizability multiplied by E. So we have obtained already our E, and it is somehow related to P. So we can write here P is equal to 4 pi epsilon naught A cubed multiplied by the electric field, the external electric field. Now, if we relate this into our equation, kini siyang equation, no? P is equal to alpha times E, then comparing these two equations, then we can say that alpha, this constant here, the atomic polarizability, is equal to this constant. Okay, so you have alpha is equal to 4 pi epsilon naught A cubed. And if we let V is equal to the volume of the atom, which is equal to 4/3 pi A cubed, since the radius of this atom is A, then your alpha can be expressed as 3 multiplied by epsilon naught times B. Okay? So this is the atomic polarizability. Now this value of alpha is accurate to within a factor of 4 for many simple atoms. But for molecules, the situation is not so simple, since molecules polarize more readily in some directions than others. Okay, so for example, carbon dioxide. Okay, so for carbon dioxide, when the external electric field is applied along the axis of the molecule, the atomic polarizability is equal to 4.5 times 10 to the minus 40 coulomb squared meter per Newton. But if the external electric field is applied perpendicular to the axis of the molecule, the atomic polarizability is different. It is equal to 2 times 10 to the minus 40 coulomb squared meter per Newton. Now, when the field is at some angle to the axis, we must resolve it into parallel and perpendicular components and multiply each by the appropriate polarizability according to this equation. So you have P is equal to the perpendicular component of alpha multiplied by the perpendicular component of the electric field plus alpha parallel multiplied by the electric field parallel. Now for a completely asymmetrical molecule, so carbon dioxide is symmetrical, okay? But for a completely asymmetrical molecule, kini siya nga equation, P is equal to alpha times E will be replaced by this equation, most general linear relationship. So we have this one, P sub x, P sub y, and P sub c. Now take note that this 9 constants here, alpha xx, alpha xy, alpha xz, and so on, this constitute the polarizability tensor, and it is dependent on the orientation of the axis that we choose. Now, it is possible to select axis such that kini siya, no? Kini siya alpha xy, alpha xc, where your I is not equal to J, mahimo ni siyang 0. So, this will vanish. Mag-vanish ni sila ng mga terms. Ang mahabilin nilang dayon kay kini Px equals alpha xx ex, Py is equal to alpha y ey, and Pz equals alpha zz ez. Okay? So, that is your constants will become 0. Depende na kung unsay orientation sa ato ang axis. Okay, so let us have some examples. So the first example is problem 4.1. We have a hydrogen atom with the Bohr radius of half an angstrom is situated between two metal plates 1 millimeter apart. So these metal plates are connected to opposite terminals of a 500 volts battery. What fraction of the atomic radius does the separation distance d amount to roughly? And estimate the voltage you would need with this apparatus to ionize the atom. Use the value of alpha in table 4.1. So this is table 4.1, and we are talking about a hydrogen atom which has polarizability alpha over 4 pi epsilon naught, which is in units of 10 to the minus 30 meter cube, equal to 0.667. We are given with the voltage, which is equal to 500 volts, and we are also given with the distance between the two metal plates, which is 100 millimeter apart. And we are also given with the radius, the Bohr radius of the hydrogen atom, which is equal to half an angstrom. Okay? So the voltage is equal to 500 volts, and then we have X. This is the separation distance between the two metal plates connected to opposite terminals of the battery, which is 1 millimeter. So this is equal to 1 times 10 to the minus 3 meter. And then we are also given with the radius of the atom, the hydrogen atom, which is equal to half an angstrom, or that is an angstrom is equal to 1 times 10 to the minus 10 meter. So that is 1 angstrom equals 1 times 10 to the minus 10 meter. So half an angstrom, that means you have 0.5 times 10 to the minus 10 meter. So let us use this given to find the following. So the first one is, what fraction of the atomic radius does the separation distance d amount to roughly? And the second one is, we have to estimate the voltage that we need in order to ionize the atom, or meaning to say, para ma-completely hindi mo siya conductor. Now, take note also that given in this table is alpha over 4 pi epsilon naught. And for hydrogen, alpha over 4 pi epsilon naught is equal to 0.667 times 10 to the minus 30 meter cube. So, first we need to find the electric field. So, what is the field, the applied field, or the external field that is applied to the hydrogen atom? Okay, so in order to do that, let us take a look at this. So, our electric field is coming from the apparatus, no? We have two metal plates that is connected to 500 volts battery. So that is the source of our electric field. So we can get the electric field, the magnitude of the electric field, by using this equation, V over X. So we have the voltage is 500 volts divided by your X is equal to 1 times 10 to the minus 3 meter. Okay, so the electric field is equal to 5 times 10 to the 5, the unit would be volts per meter or newtons per coulomb. Okay, so this is now the electric field. Now from the table, from table 4.1, we have alpha is equal to 4 pi epsilon naught, which is equal to 0.667 times 10 to the negative 30 meter cube. Okay, therefore from here, we can get alpha, which is equal to 4 pi epsilon naught multiplied by 0.667 times 10 to the minus 30 meter cube. Okay, so you have 4 pi, and then the value of your epsilon naught is 8.85 times 10 to the minus 12. The unit is, if K is equal to 9 times 10 to the 9 Newton meter squared per coulomb squared, then this is coulomb squared per Newton meter squared. Okay, so this is your epsilon naught, and then multiplied by 0.667 times 10 to the minus 3 meter cube. Alright, so your alpha is equal to 7.34 times 10 to the minus 41. The unit is, you have coulomb squared meter over Newton. Okay, so this is your alpha. So we have obtained our electric field, and then we have the atomic polarizability, and then next is to find D. So in order to find D, we have to make use of these equations. So note that P is equal to alpha multiplied by E, or it is equal to Q times D. Okay, so we can, we have the value of A, we have the value of alpha, we have the value of E, and then we can get this one. So this is just for a hydrogen atom. This is just equal to E. So it has one proton. So Q is just equal to E, which is equal to 1.602 times 10 to the minus 19 coulomb. Okay. So this is the charge of a proton. 1.602 times 10 to the minus 19 coulomb. Okay. So from this equation, we have alpha E equals E times D. Therefore, D is equal to alpha times the electric field divided by E. Okay, so substituting, we have 7.34 times 10 to the minus 41 coulomb squared meter per Newton multiplied by the electric field, which is 5 times 10 to the 5 volts per meter divided by the proton charge, which is 1.602 times 10 to the minus 19 coulomb. So this is equal to 2.29 times 10 to the minus 16 meter. Okay, so this is so small. The displacement of the atom, or the displacement of the nucleus or the proton, is equal to this one. It is very small, 2.29 times 10 to the minus 16 meter. Now, our goal is to find what fraction is this D with respect to the radius R. So, to find that, we have to divide this with R, the radius. So, we have 2.29 times 10 to the minus 16 meter divided by the Bohr radius of the atom, which is equal to 0.5 times 10 to the minus 10 meter. Okay, so this is equal to 4.6 times 10 to the minus 6. So this is our final answer. Now the other question is, to ionize the atom, what could be the value of V? So in order to ionize the atom, then it should be that your D, the displacement of the nucleus, or the positive nucleus, must be at least equal to the radius R. That is, R is equal to this one, alpha E. So since D is equal to R, then R is equal to alpha E divided by alpha times the electric field divided by the charge. So we have alpha E divided by the charge, and let us relate the electric field with the voltage. So electric field is equal to V over X. So we can replace this E here with V over X. So you have A times V over E times X. Okay. So our goal is to find V. So we have V is equal to R EX divided by alpha. Now your R is equal to 0.5 times 10 to the minus 10 meter multiplied by the electron charge, which is the proton charge rather, 1.602 times 10 to the minus 19 coulomb, multiplied by Rx, which is 1 times 10 to the negative 3 meter, divided by alpha, which is equal to 7.34 times 10 to the minus 41 coulomb squared meter per Newton. Okay, so you have V is equal to 1 times 10 to the 8 volts, or you have 1 times 10 to the 8 Newton meter per coulomb, or you have 1 times 10 to the 8 joules per coulomb. So the SI unit for voltage or the potential is volts. You can use also Newton meter per coulomb or joules per coulomb.